Today, we're talking about large concept models, or LCMS. And I know what you're thinking. LCMS, what are those? You've probably heard of large language models, right? Those are the powerhouses behind chatbots and all sorts of text generation tools. LCMS are something entirely different and really exciting.
Yeah, they're taking things to a whole new level.
What makes LCM so special?
Traditional LLMs, they work with words, one word at a time, predicting the then cat, then sat. You know the drill.
Yeah, makes sense.
LCMS, they operate on the level of concepts instead of individual words. They're dealing with entire sentences.
Hold on. So instead of predicting the cat sat, an LCM could predict the whole idea. The cat sat on the mat all at once.
You got it.
Whoa, that's mind-blowing. It is.
In this shift to concept level processing, it mirrors how we humans think.
Okay, so it's like we're moving closer to AI that actually understands meaning rather than just manipulating words.
I'm already intrigued. So tell me, what are some of the advantages of this approach? I mean, why should we be excited about LCMS?
Well, for starters, LCMS are amazing at handling long-form content. Think about it. When you're working with larger units of meaning, you can maintain coherence. You can keep the big picture in mind, something that traditional LLMs often struggle with.
So it's not just about generating grammatically correct sentences. It's about creating text that actually makes sense as a whole.
Imagine summarizing a lengthy research paper or writing a compelling story. LCMs are built for this kind of task.
Okay, I'm starting to see the potential here. But how do these LCMS actually work? Where do these concepts come from?
Good question. So this research, it relies on a pretty remarkable tool called Sonar.
Sonar.
Yeah, it's a sentence embedding space. Think of it as a way to represent the meaning of a sentence as a set of numbers.
Okay, I kind of get it. So it's like translating the meaning of a sentence into a mathematical code.
And what's really cool about Sonar is that it can handle text in 200 languages.
Wait, 200 languages?
Yep, and it can handle speech in 76 languages.
That's insane. So theoretically, this technology could work with almost any language on the planet.
That's the idea. It's a step towards truly language-agnostic AI.
Okay, my mind is officially blown. This is huge. Now, let's get a bit more technical. How do researchers actually build these LCMs?
Well, there are a few different approaches, but one that's showing a lot of promise is something called diffusion-based LCMs.
Diffusion-based LCMs?
Yeah, these models, they take inspiration from a technique used in image generation.
Oh, like those AI art generators where you give it a prompt and the image slowly comes into focus?
Exactly, but instead of pixels, we're working with concepts in the Sonar space. Imagine a concept starting as this fuzzy, noisy idea, and then gradually, through a series of steps, the model refines it and clarifies it until it becomes a clear, well-defined concept.
So Reese diffusion-based LCMs are essentially learning to extract meaning from a sea of noise.
Exactly. And it's a remarkably effective.
Wow. Okay, we've covered a lot of ground here, but I'm curious. You mentioned that working with concepts offers some major advantages over traditional LLMs. Can you walk me through some of the key benefits?
Sure. So aside from their strength in long-form content, LCMs have also demonstrated this remarkable ability called zero-shot generalization.
Zero-shot generalization? What's that?
It means they can understand and process languages they've never been explicitly trained on.
Seriously?
Yeah.
So they can understand languages they've never seen before?
Yep. Simply because the underlying concepts are language agnostic.
But how is that even possible?
It's all thanks to Sonar. It captures the essence of meaning in a way that transcends specific languages. Researchers tested this using a summarization benchmark across 42 languages, and the results were particularly impressive for languages with limited data available, like Burmese and Hausa.
Wow, that opens up some incredible possibilities for global communication and understanding. Feels like the dream of a universal translator is finally within reach.
It could be.
This is amazing. And to think we're just scratching the surface of what LCMS can do.
We are. There's so much more to explore. And one area that's particularly exciting is incorporating explicit planning into these models.
Explicit planning? What do you mean by that?
Well, the idea is to have a separate model that creates a high-level outline for the generated text before the LCM starts filling in the details with concepts.
So it's like having a blueprint before starting a construction project.
Yes, and this approach could lead to even more coherent, complex, and well-structured outputs from LCMs, especially for longer pieces of text.
I'm starting to see why you're so excited about this technology. Yeah, it feels like we're on the verge of a major breakthrough in how AI interacts with language.
I believe we are.
LCMs are truly pushing the boundaries of what's possible. Can you tell me more about the different types of diffusion-based LCM architectures?
Happy to. So we really wanted to explore, different ways to leverage this concept of gradual refinement that we were talking about. One approach is the one tower model.
One tower?
Yeah. Basically, it's a single transformer model that takes in a sequence of these noisy concept representations, and it tries to predict the clean, noise-free version of the next concept.
Okay. So it's like taking a blurry image and slowly bringing it into focus. One concept at a time.
And of course, all while keeping the preceding context in mind.
Right. So it's not just denoising, it's also understanding the flow of ideas.
Precisely. Now, then we have the two-tower model. This one uses two separate transformer models. One model called the contextualizer. It focuses on encoding the preceding clean concepts, capturing that overall context of the sequence.
Okay.
And then the other model, the denoiser, takes this contextual information and the noisy representation of the next concept and predicts its clean version.
Interesting. So the two-tower model is kind of dividing the labor, so to speak, with one model focusing on context and the other on denoising.
The researchers also experimented with different noise schedules.
Noise schedules?
Yeah. These essentially control how much noise is added at each step of that diffusion process.
I imagine finding the right noise schedule is pretty crucial. Too much noise and the model might completely lose track of the original concept. Too little noise and it might not learn to generalize effectively.
Yep. It's a delicate balancing act. They tried a variety of schedules like cosine, quadratic, sigmoid, each with its own, unique shape and characteristics.
And what did they find? Was there a clear winner?
Well, it depends on what you're looking at. Some schedules performed better on certain metrics, like contrastive accuracy.
Contrastive accuracy?
Yeah, it measures how well the model can distinguish between similar concepts. And interestingly, they observed that schedules with a wider range of noise levels tended to lead to better contrastive accuracy.
So it's like giving the model a more challenging workout, which ultimately helps it develop stronger discrimination abilities.
That's a great way to put it. They also investigated how different loss functions, which essentially guide the model's learning process, affect the results.
Right. So they didn't just play with the noise, but also with how the model learns from its mistakes.
Precisely. For instance, they explored weighting the loss function to give less emphasis to fragile concepts, those that are more sensitive to noise and prone to causing errors.
So it's like trying to shield the model from those particularly unstable concepts so it can focus on learning the more robust ones.
Exactly.
Clever. So after experimenting with all these variations, what were the main takeaways? Which approach kind of emerged as the most promising?
Well, across the experiments, the two-tower diffusion-based LCM consistently outperformed the other architectures. It seems that having those dedicated models for context and coding and denoising really allows for a more nuanced and effective learning process.
That's fascinating. It really highlights the importance of carefully designing the architecture of these models to match the complexities of the task at hand.
They also did some qualitative analyses. Having the model generate stories based on prompts, and the coherence and quality of the narratives were really impressive, on par with what you'd expect from a traditional LLM of comparable size.
So not only can LCMS handle long-form content and understand new languages, they can also craft compelling stories.
And remember, this was achieved without explicitly training the model on storytelling tasks. It learned this ability simply by grasping the underlying concepts embedded in the data it was trained on.
Yeah, it really speaks volumes about the power of this concept-driven approach. But what about those fragile concepts you mentioned earlier? How much of a hurdle do they pose to the development of truly reliable LCMS?
It's a valid concern and one that researchers are actively addressing. Imagine the Sonar embedding space as this vast map where each point represents a concept. Ideally, the distances between these points would accurately reflect the relationships between the concepts.
So concepts that are closely related in meaning would be clustered together on this map.
Exactly. But the reality is that this Sonar space isn't perfect. Sometimes two concepts that seem close together on the map might actually have very different meanings. And even a tiny shift in a concept's embedding, like nudging a point slightly on the map, can drastically alter its meaning when decoded back into text.
So you might end up with a sentence that's grammatically correct but makes no sense semantically.
Precisely. And this fragility can lead to inconsistencies and errors in the model's output.
Right. So how are researchers tackling this problem?
One approach is to fine-tune the decoders, which are responsible for translating those concept embeddings back into text to be more robust to these small perturbations in the embedding space.
So training them to be more forgiving, to recognize that a slightly misplaced concept might still have a valid meaning.
Another strategy is to carefully filter the training data to remove concepts that are known to be particularly fragile. It's like cleaning up the map by getting rid of those points that are prone to causing confusion. Okay. And they're also investigating ways to incorporate information about fragility directly into the training process so the model can learn to avoid those problematic concepts altogether.
It sounds like a multifaceted approach is needed to tackle this challenge. But it's encouraging to know that researchers are aware of the issue and actively working on solutions.
Fragility is a hurdle, but it's not insurmountable. The potential benefits of LCMS are too significant to ignore, and the research community is committed to pushing the boundaries of what's possible with this technology.
We've talked about the how and the why of LCMS, how they work and the advantages they offer. Let's step back for a second and think about the bigger picture. Well, what does this all mean for the average person? How could this technology actually change our lives?
Well, that's the really exciting part. The potential applications of LCMS are vast. I mean, imagine a world where language barriers are virtually eliminated.
And no more awkward Google Translate phase.
Exactly. We could have real-time translation tools that accurately convey not just the words, but the nuances, the cultural context behind them. Yeah, I think
That would be incredible. It would revolutionize communication and understanding across cultures.
it really would. And think about education. LCMS could personalize learning experiences, adapting to individual students' needs and helping them grasp complex concepts in a way that's intuitive and engaging.
It's like having a personal tutor who speaks your language literally and figuratively.
And then there's the creative potential. Imagine writers collaborating with AI that can not only generate text, but understand the emotional undertones and narrative structures of their stories. Or musicians working with AI that can compose melodies that evoke specific feelings and themes.
Wow, it's an exciting time to be alive. Thank you for joining us today. We hope this episode has sparked your curiosity and inspired you to learn more about this fascinating field. Until next time.